swallowed by a landscape where more than 95% of the land is desert, and natural freshwater resources are almost completely depleted. Saudi Arabia was forced to launch one of the most ambitious infrastructure megaprojects of the 21st century, building a massive water pipeline network to transform barren desert into agricultural land capable of producing millions of tons of food every year. This is not only a battle against the desert, but also an effort to redefine a new model of agriculture for the future. So how did Saudi Arabian engineers and farmers build invisible steel rivers that brought life to an entire agricultural empire in one of the harshest deserts on Earth? That is the engineering miracle we will explore in today's video. Covering more than 2.1 million square kilometers, Saudi Arabia is one of the largest countries in the Middle East. Yet more than 95% of its territory is desert, forcing a population of more than 37 million people to cluster along the coastlines of the Red Sea and the Persian Gulf. In many regions, the average annual rainfall is less than 100 millimeters, while summer temperatures regularly exceed 45 degrees Celsius. Rivers are virtually non-existent, surface water has almost disappeared, and groundwater aquifers have been severely depleted after decades of extraction. This has left Saudi Arabia facing an unprecedented paradox. The country possesses the resource the entire world desires: oil. But the one resource it lacks is water. Despite sitting on more than 260 billion barrels of oil, it still has to spend billions of dollars just to produce every drop of fresh water. In the Middle East, oil builds empires, but water is what determines which nations can survive in the long term. That is why the country began developing one of the largest water infrastructure systems in the world, connecting giant coastal desalination plants to a water pipeline network stretching more than 12,000 kilometers, more than twice the length of the Nile River, forming a vast distribution system that reaches deep into the interior. More than just solving the challenge of supplying drinking water, this network has unlocked an even greater ambition: transforming barren deserts into industrial-scale agricultural regions capable of producing millions of tons of food every year. But to move water across thousands of kilometers through one of the harshest deserts on Earth, Saudi Arabia first had to build rivers made of steel. The journey that carries seawater across the desert begins with a massive network of steel pipelines. To withstand continuous high pumping pressure, underground impact, and the extreme heat of the desert, these pipelines must meet exceptionally demanding engineering standards. That is why they are typically manufactured from high-strength carbon steel, the same material widely used in the oil and gas industry. The process begins with enormous rectangular steel plates, pre-cut to precisely calculated dimensions. Each plate is large enough that, once rolled, it forms a pipe with a diameter of about 1.8 meters and a wall thickness of nearly 25 millimeters. The steel is then fed through a multi-roll forming machine. Industrial rollers gradually press and bend the plate until the flat sheet becomes a complete cylinder. Once the two edges meet, the pipe blank is ready for the most critical stage: longitudinal seam welding. Here, automated welding robots travel along the entire length of the pipe, creating a joint strong enough to withstand continuous water pressure for many years. After welding, the pipe is cooled with water, precision ground to remove burrs and correct dimensional deviations, and then both ends are beveled to standard specifications, allowing faster assembly, tighter connections, and greater pressure resistance in the field. At staging yards, every batch of pipes is labeled and organized according to the exact installation sequence to prevent delays during field construction. Each pipe section is typically about 12 meters long, and weighs up to 40 tons. This length was not chosen at random. It represents the optimal balance between engineering requirements, system reliability, transportation efficiency, and installation along long-distance routes crossing the desert. Even a single pipeline stretching 1,000 kilometers requires more than 80,000 pipe sections, turning logistics into a massive industrial operation. Once every final coordinate has been confirmed, an invisible road begins to emerge across the heart of the desert. First, the entire surface along the pipeline route is leveled and widened into a corridor about 40 meters across, providing enough space for heavy machinery, material storage areas, cranes, and multiple construction crews to operate simultaneously. Next, heavy excavators begin digging trenches to the exact design elevation. The trenches are typically 2 to 3 meters deep, providing sufficient protection for the pipeline against surface temperatures, vehicle loads, and external environmental impacts. But the desert is not made of sand alone. Many areas consist of solid bedrock or semi-mountainous terrain, where conventional excavator buckets are almost useless. In these locations, construction crews must drill holes, place industrial explosives, and carry out controlled blasting in stages to clear a path for the pipeline. Once the trench is complete, the sharp rocks and uneven ground still cannot support the pipeline directly. A bedding layer of fine sand or fine granular material is first placed along the bottom of the trench, creating a uniform cushion that reduces localized pressure points and minimizes stress on the pipeline throughout decades of operation. But even after the trench is ready, the real challenge begins when 40-ton steel sections must be lowered into position with centimeter-level precision. Each pipe section is positioned using cranes. Before welding, a 360-degree hydraulic internal clamp is inserted inside the pipe to align both ends perfectly and maintain absolute concentricity. Even the slightest misalignment can create flow turbulence, increase stress, and shorten the service life of the entire pipeline. Once both pipe ends are secured, the automated welding system begins traveling around the circumference of the joint. But speed means nothing if the weld is not flawless. Every joint is therefore inspected using industrial ultrasonic testing to detect hidden cracks, internal voids, or alignment defects that cannot be seen with the naked eye. After inspection, the welded joint is coated with multi-component epoxy to restore the corrosion protection layer for the decades ahead. Only then do tracked side boom machines move along the construction site, lifting the entire steel assembly with wide slings before lowering it into the trench centimeter by centimeter to prevent bending or damage to the protective coating. The final stage is multi-layer backfilling. Fine sand is placed first to protect the pipe surface, after which soil and rock are added and compacted layer by layer, gradually burying the entire steel river beneath the desert to ensure long-term stability for decades. But at this point, Saudi Arabia has only finished building the road. It still has not created the water. Everything begins with the vast, seemingly endless blue ocean offshore. Instead of drawing seawater close to the coastline, where sand, oil, plankton, and pollution are more concentrated, desalination plants typically place offshore intake systems several hundred meters to a few kilometers from shore, in deeper, more stable waters. Once inside the plant, the seawater passes through 2 stages of coarse and fine screening to remove all impurities, from large debris to small marine organisms and remaining organic matter before entering the treatment system. But the most dangerous contaminants are almost invisible. To remove fine sand, silt, and suspended particles that could damage pumps and filtration membranes, the seawater passes through a multi-layer sand filtration system, reducing turbidity from 5 to 20 NTU to less than 1 NTU. Next, the water is treated with chemicals to disinfect it and coagulate suspended particles before passing through 1 to 5 micron cartridge filters, the final protective barrier for the expensive reverse osmosis membranes. Then the water reaches the heart of the entire system, reverse osmosis. To separate salt from seawater, Saudi Arabia uses high-pressure pumps operating at 55 to 70 bar, forcing water against its natural osmotic direction through ultrafine reverse osmosis membranes, where only water molecules can pass, while salt, bacteria, and impurities are left behind. Before entering the distribution system, the water is remineralized and its pH is adjusted to ensure chemical stability. It is then produced continuously 24 hours a day, 7 days a week, at a scale of nearly 16 billion liters per day, making Saudi Arabia one of the world's largest desalination producers. For Saudi Arabia, desalination has never been the final destination. It is only the first step in transforming seawater into green farmland across one of the harshest deserts on Earth. Water from the massive pipeline network is quickly delivered to the desert to serve an even greater goal: achieving food security. Within just a few decades, giant green oases spread across more than 11,000 square kilometers of desert, creating one of the world's largest center-pivot irrigation systems. Throughout the growing season, automated irrigation systems continuously adjust the amount of water according to the crop's needs before combine harvesters complete the entire harvesting process. By the late 1980s, Saudi Arabia was producing more than 4 million tons of wheat every year, not only becoming fully self-sufficient in domestic demand, but also exporting wheat to international markets. However, this success also led to the excessive depletion of groundwater aquifers, forcing the country to gradually end its wheat self-sufficiency program and shift toward cultivating higher-value crops. That was also the moment when the precious water flowing through the desert was redirected to an agricultural industry that has been part of Saudi Arabia for thousands of years: date palm cultivation. In regions such as Al-Qasim, Al-Asa, and Medina, millions of date palm trees are planted in perfectly aligned rows, forming one of the largest date-producing regions in the world. Drip irrigation systems deliver water precisely to the base of each tree, while sensors continuously monitor soil moisture to minimize water loss. When the harvest season arrives, specialized lifting vehicles raise workers to the tops of trees, standing more than 10 meters tall, where they cut individual date clusters weighing tens of kilograms. At many large plantations, hydraulic lifting platforms and mechanized equipment have replaced most traditional climbing work. Today, Saudi Arabia is one of the world's largest date producers, with an annual output of more than 1.5 million tons and exports reaching more than 100 countries. This industry not only generates hundreds of millions of US dollars in export revenue, but has also become one of the pillars of Saudi Arabia's agricultural economy. It stands as the clearest proof of how water infrastructure and technology have transformed the desert into a large-scale agricultural powerhouse. Water has not only transformed the desert into farmland, but has also made it possible for Saudi Arabia to build one of the most advanced dairy industries in the world. Al-Marai alone, the largest dairy company in Saudi Arabia, operates nearly 200,000 dairy cows across 8 industrial-scale farms. Even more remarkable, each cow produces an average of more than 12,400 liters of milk per year, exceeding the average productivity of many countries with highly developed dairy industries, including the United States and New Zealand. To protect the herd from the extreme desert heat, The barns are equipped with powerful ventilation fans, evaporative cooling pads, and misting systems, maintaining suitable temperatures for the cattle throughout the year. More than 12,000 kilometers of pipelines, dozens of desalination plants, vast wheat fields, date plantations, and modern dairy farms have demonstrated that even a country where more than 95% of the land is desert can build a large-scale agricultural industry if it can solve the challenge of water. Do you think projects like this represent the future of agriculture in the world's arid regions? The paradox of Japan is that the very advantages that created its prosperity have also become its greatest vulnerability. Surrounded by the ocean and blessed with more than 35,000 kilometers of coastline, Japan has been forced to concentrate most of its population, major cities, seaports, industrial zones, and its most fertile plains along the Pacific coast. Yet this same coastline sits at the convergence of four major tectonic plates, making it one of the most seismically active regions on Earth. Whenever the seafloor is displaced by a powerful earthquake, the entire column of water above it is pushed upward, generating tsunami waves capable of traveling at speeds of nearly 800 kilometers per hour. As they move into shallow coastal waters, the waves rapidly increase in height, transforming into enormous walls of water that surge directly onto the land. That is why Japan has repeatedly suffered some of the most devastating tsunamis in the world. The disaster in 2011 alone claimed the lives of more than 18,000 people, destroyed more than 123,000 buildings, and triggered the most severe nuclear crisis since Chernobyl. Total economic losses exceeded $220 billion, making it the costliest natural disaster in modern history. But that was not the only price Japan had to pay. With only about 12% of its land suitable for cultivation, every major tsunami devastates precious coastal plains while threatening the limited farmland that feeds the entire nation. Instead of simply responding after disasters, the Japanese turned adversity into a catalyst for innovation, building one of the most advanced disaster defense systems in the world. So how can this Great Wall, stretching nearly 400 kilometers, protect millions of people, safeguard agricultural regions that produce millions of tons of crops every year, and defend the world's fourth largest economy? To understand this extraordinary achievement, we must first go back to the moment when Japan decided to do what many believed was impossible. The first step was to create the most detailed tsunami risk map ever developed. Engineers gathered dozens of layers of data, including records of earthquakes and tsunamis spanning centuries, seafloor topography, ocean depth, the shape of coastal bays, shoreline gradients, and the locations of cities, seaports, industrial zones, and critical agricultural plains. This information was then fed into hydrodynamic models running on supercomputers. Instead of simulating a single scenario, the system calculated thousands of different possibilities. Based on these simulations, engineers determined the height, length, location, structural design, and level of reinforcement required for each section of the wall, ensuring it is tailored to the terrain and tsunami risk of every coastal area. In other words, Japan's Great Wall was not built to follow the coastline. It was built to follow the path of risk. For Japanese engineers, the first enemy was not the tsunami, but the unstable coastal ground itself. After thousands of years of sediment deposition, many coastal areas were formed from sand, mud, and soft sediments that could not support the enormous weight of massive concrete seawalls. In areas with weak ground conditions, reinforced concrete piles or steel piles measuring between 20 and 40 meters in length were driven or drilled into stable soil layers, transferring the entire load of the wall to the foundation below. In many locations, the ground was further reinforced with crushed stone, geotechnical materials, or advanced soil improvement technologies to reduce settlement and prevent soil liquefaction during earthquakes. Only after the foundation was strong enough could construction of the tsunami seawall truly begin. Instead of pouring concrete continuously along the entire length of nearly 400 kilometers, engineers divided the project into thousands of independent sections. This allowed construction to proceed simultaneously at multiple locations while limiting the impact if any section were damaged in the future. First, reinforced steel cages were assembled directly at the construction site and positioned on the completed foundation system. Next, high-strength concrete was continuously pumped into the formwork using specialized concrete pump trucks. Every layer of concrete was mechanically vibrated to remove air pockets, increase density, and minimize cracking after curing. Once the concrete reached its designed strength, the individual sections were connected to form a continuous defensive barrier. Depending on the terrain and the level of tsunami risk, the wall ranges from 5 to 15 meters in height, while its foundation is anchored as deep as 25 meters below the surface. The base of the wall is also significantly widened to distribute structural loads, resist overturning and sliding, and reduce erosion under the immense force of tsunami waves. However, the purpose of the wall is not to defeat the ocean. In many locations, additional layers of large armor rocks, wave-dissipating concrete blocks, and reinforced sloped embankments are installed in front of the wall. These structures absorb part of the wave's energy before it reaches the seawall itself, while also reducing foundation erosion and extending the lifespan of the entire defense system. Interestingly, the Japanese have never considered the Great Wall to be their only line of defense. If a tsunami powerful enough were to strike, no wall could guarantee stopping millions of tons of water rushing toward the land. Instead of trying to conquer nature, the Great Wall is designed to slow it down. By reducing the height of the waves, absorbing part of their energy, and delaying their arrival by just a few minutes, the early warning system gains enough time to issue alerts, evacuation routes can be activated, and millions of people have a chance to escape the danger. That is why, behind the wall, an entire network of seismic sensors, wave monitoring buoys, warning sirens, and evacuation routes operates as one unified system. But the greatest value of this defensive barrier is not the wall itself. It is what the wall protects behind it. It protects Japan's limited coastal plains, which produce millions of tons of agricultural products every year and help sustain one of the most productive agricultural systems in the world. With about 80% of its territory covered by mountains, Japan has only about 12% of its land suitable for cultivation. Most of this limited farmland is concentrated on fertile coastal plains, the very areas that face the constant threat of earthquakes and tsunamis. That is why every square meter of land behind the Great Wall carries extraordinary importance for the nation's food security. Among these precious resources, rice has always been regarded as Japan's second line of defense. During harvest season, GPS-guided combine harvesters automatically move through the rice fields with an accuracy of just a few centimeters, cutting, threshing, and cleaning the grain in a single operation. This highly mechanized process speeds up harvesting, reduces crop losses, and preserves grain quality before the rice is dried, milled, and sorted. Every year, more than 1.4 million hectares of rice paddies produce approximately 7 to 8 million tons of rice, supplying the primary food source for more than 120 million people across Japan. Unlike many countries that can expand their agricultural land, Japan has virtually no additional farmland to replace its coastal plains if they are devastated by tsunamis or contaminated by saltwater. In a country where expanding farmland is almost impossible, the value generated from every square meter matters more than total production. and Wagyu is perhaps the clearest example of that philosophy. With limited land available for livestock farming, Japan does not compete by raising larger cattle herds like the United States or Brazil. Instead, the country focuses on genetic selection, herd management, and quality optimization to produce one of the world's most valuable types of beef. For approximately 28 to 36 months, the cattle are fed carefully formulated rations consisting of hay, rice straw, corn, barley, and various energy-rich grains. This controlled feeding program regulates growth while encouraging the formation of the fine marbling that develops throughout the muscle. The extended feeding period creates Wagyu's signature tenderness, rich flavor, and its world-famous melt-in-your-mouth texture. For Japan, Wagyu is far more than just beef. It is a multi-billion-dollar industry with a domestic market worth nearly $11 billion and annual exports exceeding $400 million, making Japan the global leader in the premium beef segment. Even after protecting its land from tsunamis, Japan still faced another major challenge: too little farmland and an increasingly aging agricultural workforce. Instead of expanding agricultural land, the country chose to increase productivity on every square meter through high-tech greenhouses. Today, Japan operates approximately 43,200 hectares of greenhouses, producing a large share of the nation's premium vegetables, fruits, and flowers. Transparent glass panels and advanced polymer materials maximize the use of natural sunlight, while automated shading, ventilation, heating, and cooling systems continuously regulate temperature and humidity to maintain optimal growing conditions throughout all 4 seasons. Many greenhouses also incorporate hydroponics, fertigation, and autonomous robots for planting, harvesting, and transporting crops. As a result, water consumption can be reduced by as much as 70 to 90%, while productivity per square meter is many times higher than that of open field farming. Inside these facilities, premium melons, strawberries, tomatoes, and leafy vegetables are produced year-round with highly consistent quality for both domestic and export markets. One of the most remarkable examples is the Bison strawberry, one of the most expensive fruits in the world. After more than 15 years of breeding, only about 500 strawberries meet the standards for sale each year, with prices reaching as high as $500 per fruit. What Japan is selling is not just a strawberry, but years of breeding research, precision greenhouse technology, and nearly perfect quality standards for size, color, aroma, and sweetness. From rice and Wagyu to high-tech greenhouses, they all share one thing in common: they depend on the limited land that Japan must protect at all costs. No wall can completely defeat a tsunami, but by buying even a few precious extra minutes, Japan's Great Wall helps protect its people, its farmland, and one of the highest value agricultural systems in the world. For centuries, Sargassum, one of the vital links that created vast biological oases and sustained the balance of the Atlantic Ocean ecosystem, has now begun pushing that very ecosystem toward the brink of collapse. In its natural state, Sargassum existed almost exclusively around the Sargasso Sea, a body of water spanning more than 5 million square kilometers in the North Atlantic, nearly half the size of Europe. The turning point came when the conditions that had once kept Sargassum under control gradually disappeared. As ocean temperatures rose due to climate change, millions of tons of fertilizers and agricultural waste were continuously washed from the Amazon, Congo, and Mississippi rivers into the Atlantic Ocean. Combined with shifting ocean currents, these factors unintentionally created the perfect environment for Sargassum to explode on an unprecedented scale. Today, the total mass of Sargassum has surpassed 37 million tons, forming the Great Atlantic Sargassum Belt, one of the largest biological disasters ever recorded on Earth. Seen from space, many scientists have described it as a brown monster spreading across the Atlantic Ocean. The greatest danger begins when Sargassum starts to decompose. It releases hydrogen sulfide, a toxic gas with the smell of rotten eggs that can irritate the lungs and affect the nervous system. In Mexico and throughout the Caribbean, many tourist beaches are forced to close for weeks during Sargassum season, causing billions of dollars in losses every year. But today, the very thing that makes Sargassum a disaster is also what makes it extraordinarily valuable. Perhaps the greatest irony is that this biological nightmare is gradually becoming a new source of raw materials for the post-carbon civilization. And it is here that the race to harvest one of the ocean's largest biomass resources officially begins. Unlike oil or mineral resources that can be stored for years, Sargassum retains its value for only a very short period of time, forcing countries along the Atlantic coast to collect millions of tons of seaweed before it has a chance to rot. At first, Sargassum is collected directly from the beaches using excavators and mechanized conveyor systems before being transported to coastal processing facilities. These systems operate like giant biomass screening machines, collecting the seaweed while removing much of the sand and seawater right on the beach. During the 2018 outbreak alone, the Caribbean spent around $120 million clearing Sargassum from its coastlines. Meanwhile, South Florida once estimated that cleanup costs could reach as much as $40 million every year to protect its tourist beaches. Few people are willing to do this job. For many workers, the worst part is not the weight of the seaweed, but the overwhelming smell of hydrogen sulfide mixed with the odor of sewage. But collecting Sargassum on the beaches quickly revealed its limitations. Bulldozers often remove large amounts of beach sand along with the seaweed, increasing the risk of coastal erosion and damaging shoreline ecosystems. At the same time, the volume of Sargassum washing ashore in the Caribbean has been estimated to reach as much as 10,000 wet tons per day during peak periods, equivalent to 400 truckloads of biomass. That is when the battle began moving offshore, as humans took the initiative to hunt ocean waste. The process usually begins with floating barriers stretching for hundreds of meters, deployed parallel to the coastline to intercept incoming Sargassum and concentrate it into dense biomass corridors. Specialized harvesting vessels then travel along these biomass corridors, using floating conveyor belts and pumping systems to continuously lift the seaweed into onboard storage holds. Some harvesting vessels operating in Mexico and the Caribbean can now collect between 40 and 100 tons of Sargassum per day. Compared with collecting it directly from the beaches, offshore harvesting keeps the biomass fresh, preserving the value of its cellulose, alginate, and organic carbon, critical components for the biomaterials and biofuel industries. But harvesting is only the beginning. The real challenge is how to transform this chaotic mass of biomass into a stable raw material suitable for large-scale industrial production. One of the companies leading this race is Sargassum, a Mexican startup striving to transform millions of tons of Sargassum into construction materials for the promising low-carbon economy. Omar de Jesus Vasquez Sanchez started the business almost from nothing, beginning with small teams of workers collecting seaweed along Mexico's coastline. The Sargassum brick-making process usually begins as soon as the Sargassum is transported from coastal collection sites to the factory. Containing nearly 90% water, the freshly harvested seaweed is first washed under high-pressure water to remove salt, sand, and organic debris. It is then sun-dried or mechanically dried until its moisture content is reduced to around 10 to 20%. The seaweed is then shredded into fine biomass fibers and blended with clay, lime, biopolymers, or cement according to proprietary formulations to create a durable biocomposite mixture. The biocomposite mixture is then fed into high-pressure molding machines capable of producing nearly 500 bricks per hour. The finished bricks are approximately 3 times lighter than conventional concrete, significantly reducing transportation costs and the structural load of buildings. Once home to countless marine creatures across the Atlantic Ocean, Sargassum is now becoming a home for low-income families in Mexico. Thanks to its natural fibrous structure, which traps air inside the material, homes built with Sargassum bricks can reduce indoor temperatures by approximately 5 to 7 degrees Celsius during the summer, while providing more stable insulation throughout the winter. To date, more than 13 homes have been built using this material, with each one reusing nearly 20 tons of Sargassum. And that is precisely why the construction industry has begun paying attention to Sargassum. The cement industry alone currently emits more than 2.5 billion tons of carbon dioxide every year, while Sargassum represents a free biomass resource, with tens of millions of tons continuously washing ashore across the Caribbean and North America. But turning Sargassum into a stable construction material remains a complex engineering challenge, as this biomass carries potential contamination risks and may pose long-term health concerns. And although the future of Sargassum in the construction industry remains the subject of considerable debate, many companies now see this ocean biomass as a promising solution to replace hundreds of millions of tons of petroleum-based plastics. Every year, the world produces more than 400 million tons of plastic, most of it made from petroleum, and around 11 million tons of that eventually end up in rivers, lakes, and oceans as plastic waste. That is also why the bioplastics industry is pursuing an even greater ambition, transforming Sargassum into a direct replacement for single-use plastic packaging. Thanks to its natural film-forming properties, Sargassum can be washed to remove salt, ground into fine particles, and processed to extract natural polymers before being manufactured into biodegradable films, packaging materials, and food containers that naturally decompose after use. Beyond bioplastic packaging, Sargassum is also being researched for the production of textile materials, organic fertilizers, cosmetics, and many other high-value biomaterials. However, this is also what creates the greatest challenge. Unlike algae biomass cultivated under stable conditions, Sargassum continuously changes its biological composition with the seasons, making polymer extraction far more complex and much more difficult to standardize for large-scale industrial production. But biological materials are still not the final destination. The true gold mine of this ocean biomass lies in its ability to transform tens of millions of tons of Sargassum into a renewable energy source for the future. To transform Sargassum into fuel, the entire biomass is first shredded and dried before being fed into anaerobic digestion systems, where microorganisms break down the organic compounds contained within the biomass. In an oxygen-free environment, billions of microorganisms continuously decompose the seaweed to produce methane and biogas, which can then be used to generate electricity, provide heating, or be further refined into industrial fuels. Surprisingly, if approximately 1 million tons of dry Sargassum were processed, the methane produced could theoretically generate enough electricity to power around 30,000 to 40,000 households for an entire year. In the Caribbean, Dr. Legina Henry is pursuing an idea that was once considered crazy, transforming the foul-smelling seaweed covering the coastline into fuel for transportation and the energy systems of the future. Her research team has experimented with blending Sargassum with wastewater from the rum industry and blackbelly sheep manure before feeding the mixture into anaerobic digestion systems to produce biomethane. The resulting gas is then purified by removing carbon dioxide, hydrogen sulfide, and other impurities before being compressed under high pressure into bio-CNG, a fuel that can be used directly in natural gas vehicles and industrial power generators. Some early trials suggest that bio-CNG could reduce fuel costs by nearly half compared with conventional gasoline. Meanwhile, the energy produced from approximately 1 ton of dry biomass is enough to power a natural gas vehicle for more than 120 to 150 kilometers. In a more distant future, if what was once dismissed as ocean waste can become fuel for transportation, it may also become part of a low-carbon energy system capable of powering the industries of tomorrow. And as Sargassum begins to be recognized as a strategic biomass resource, the game across the Atlantic is rapidly changing. From Mexico and the Caribbean to the Gulf Coast of the United States, startups and coastal governments are racing to build Sargassum supply chains in an effort to gain control of this enormous marine feedstock. Because in the low-carbon economy of the future, controlling ocean biomass may also mean controlling fuels, biomaterials, and part of the new energy infrastructure of the 21st century. From a biological disaster in the Atlantic Ocean, Sargassum is gradually becoming a test of humanity's ability to transform the climate crisis into the post-carbon economy of the future. So what do you think? Is Sargassum truly a new goldmine for the green economy, or is it simply an experiment that is too ambitious? Share your thoughts in the comments below. After mating, female bison enter a pregnancy period lasting around 9 months. Typically, the mother gives birth to a single calf in late spring or early summer of the following year, entirely through natural instinct without human intervention. Remarkably, only about 30 minutes after birth, a bison calf is already able to stand up and follow its mother, a clear demonstration of the powerful survival instincts of this wild animal. But to raise hundreds of thousands of animals for the modern premium red meat industry, ranches across the United States still have to develop specialized care and management systems designed specifically for young bison. At modern bison ranches, calves are closely managed during their first 6 months of life, the fastest growth stage of their development. From weighing only around 20 to 30 kilograms at birth, a bison calf can reach more than 150 kilograms in just half a year. At around 4 to 6 months old, they begin weaning and transition to a diet rich in natural grasses, hay, and supplemental grains. The key to raising hundreds of thousands of high-quality bison lies in combining controlled ranch systems with natural free-range grazing across vast landscapes. It is this combination of modern management and constant natural movement that creates the lean muscle, low-fat content, and distinctive flavor that make bison meat one of the most premium red meats in the United States. Although most bison today live inside tightly managed ranches, their primitive wild instincts have almost never disappeared. Female bison still choose to raise their calves across vast and dangerous landscapes, where survival skills are forged from the very first days of life. From the moment they are born, bison calves must learn how to keep up with the herd across enormous grasslands, respond quickly to warning signals from their mothers, and even practice swimming through fast-moving rivers. All of these are essential survival skills in a harsh environment that has never been fully domesticated. Despite their massive and rugged appearance, bison are actually highly emotional animals. For many ranchers in Montana or South Dakota, bison are far more than livestock. After years of living alongside the herd, some ranchers say certain bison begin recognizing familiar truck sounds, the smell of food, or even the caretakers who regularly appear across the prairie. Although they do not possess the complex intelligence of dolphins or crows, they still display a remarkable form of survival intelligence. In particular, when living in a safe and stable environment, bison become extremely curious, exploring and interacting with their surroundings like children discovering the world for the first time. With ranches spanning thousands of hectares, controlling bison herds has never been a simple task. Today, many modern ranches have begun using drones to monitor herd movement, detect unusual behavior, and help manage feeding operations on a massive scale. After only around 2 years, a young bison calf can develop into a giant weighing nearly 1 ton, with the enormous shoulder hump that almost no other livestock species can rival. Although they are raised in semi-wild conditions and spend most of their lives outdoors, bison still need to be gathered periodically for health inspections, vaccinations, and growth monitoring. From 2 to 4 times each year, American ranchers use trucks, ATVs, and horseback riders to gradually herd the bison back toward the ranch's central handling facilities. Each individual is fitted with an electronic ear tag, assigned a unique identification number, and managed through a personal record system. But controlling animals weighing nearly 1 ton has never been a simple task. To ensure the safety of both the bison and the handlers, modern ranches use a specialized restraint system known as a squeeze chute. Built from ultra-durable steel, this device gently compresses both sides of the bison's body to keep the animal still for a short period of time, preventing sudden charges or violent movements that could destroy fences and cause severe injuries. Without this device, how many people do you think it would take to restrain one of these incredibly powerful giants? Once fully grown, bison are typically divided into one of 2 main paths: becoming breeding stock for commercial reproduction or entering the premium red meat supply chain. Each year, around 8,000 to 10,000 bison are sold at specialized auctions across the United States and Canada, based on factors such as age, breed, weight, genetic background, and reproductive potential. The growing demand for bison meat has caused the economic value of this animal to surge in recent years. Compared to the massive industrial beef industry, bison meat production remains relatively small, a factor that has helped this lean, high-protein, and near-naturally raised meat become a premium product across North America. As a result, a high-quality breeding animal can be sold for anywhere between $3,000 and more than $20,000 USD. Meanwhile, most of the remaining animals enter the red meat industry, where hundreds of bison are processed every day to meet rapidly growing global demand. After nearly 2 years roaming across the vast grasslands of North America, the journey of most bison ultimately ends at meat processing facilities.
Truly do have zero waste.
There, they are brought into a tightly controlled environment where temperature, sanitation, and the entire operational process are carefully monitored.
Tendons, the skull, the hide.
After stunning and bleeding, the carcass moves into the skinning stage. An initial incision is made using a specialized knife from the groin up to the chest before the enormous thick hide is separated from the body along the limbs. While the large-scale beef processing industry in the United States relies heavily on automated machinery and conveyor systems, bison processing is significantly different. Due to their massive size, difficult to control strength, and much lower production volume, most bison processing is still performed manually by skilled workers using highly precise cutting techniques.
Taking a step back, the way these animals were raised up.
The meat is then divided into various commercial cuts. Premium sections such as chuck eye, short ribs, and lean round are especially valued for their dense muscle structure, low fat content, and richer flavor compared to conventional beef. It is this relative rarity, combined with near-natural ranching methods, that has gradually turned bison meat into one of the most premium red meat products in North America, with prices ranging from $20 to more than $50 USD per pound. And so after spending more than a century on the brink of extinction, bison today have not only returned to revive the Great Plains, but have also become the foundation of a multi-billion-dollar red meat industry.
The bison bar.
And perhaps the most difficult question is this: if bison no longer carried economic value, would they still be conserved on such a massive scale today? From the vast grasslands of North America, our next journey will take us to the Arctic, where reindeer herding still survives in one of the harshest environments on Earth.